road vehicles to jet aircraft. From everyday applications, such as bath taps and domestic appliances, to specialized applications, such as this heat-seeking camera and these musical instruments. Products relying on brazed joints are all around us. Brazing can produce sound, leak-tight joints, often with special properties. The brazed joints in this jet engine, for example, have to resist corrosion and extremes of temperature. Welding techniques are widely taught and understood, but the versatile brazing process is often neglected. The purpose of this video is to show by practical demonstration the art of successful brazing. Brazing is a thermal joining process which can be used to join almost any combination of metals using heat and a filler metal. It produces low-cost, high-strength joints without damaging the properties of the parent materials. The major differences between brazed and other types of thermal joints are the joint design, the temperature reached during the joining process, and the filler metal used. Welded joints typically use a V preparation, and the parent metals are melted during the heating process, leaving a heat-affected zone around the finished joint. Filler metals are usually used, although this is not always necessary. In bronze or braze welded joints, a V preparation is again used, but in these cases, a filler metal based on copper and zinc, which melts at about 900 degrees centigrade, is used to build up a fillet. Brazed joints, on the other hand, incorporate close-fitting parts which are joined without melting the parent metals. The filler metal melts at a temperature above 450 degrees centigrade and is drawn through the joint by capillary attraction. Soft soldering is a similar process, but uses a filler metal which melts below 450 degrees centigrade. So the main features of brazing are: the parent metals are not melted, the filler metal melts at a temperature above 450 degrees centigrade, and the filler metal is drawn through the close-fitting joint by capillary attraction. A simple demonstration will show how a typical brazed joint is made. In this case, a steel and brass plate are being joined together. First, the mating surfaces are cleaned with a medium-grade abrasive. Flux is applied to both surfaces to prevent oxidation during the heating process. The parts are held firmly together by a simple jig. The assembly is then heated broadly and rapidly with an oxyacetylene torch. As the temperature of the parts rises, the flux becomes clear and watery, indicating that brazing temperature has been reached. The filler metal is then touched to one end of the joint. Heat from the parts melts the rod, and filler metal is drawn along the line of the joint. The assembly is now complete and needs no further heating. A quick dip in a bath of water is all that's required to remove the flux residue. Close examination of the joint shows that the fillet of brazing alloy is so fine that it can hardly be seen. Yet, the joint is very strong. A microscopic section across the joint would show a thin layer of filler metal metallurgically bonded to the two parent metals. This layer is only a fraction of a millimetre thick, but the bond is very strong. Its actual strength can be measured in a laboratory test. In this instance, a copper to steel lapped joint is being tensile tested. A pulling force is applied to both ends of the assembly. As the load increases, the copper begins to stretch until it finally breaks, but the joint is still intact. This test clearly demonstrates that a properly made brazed joint can be stronger than the parent metals used in its construction. However, this does rely on the ability of the filler metal to wet and flow completely throughout the joint area. The force which pulls the filler metal through the joint is capillary attraction. Capillary attraction is the force based on surface tension, which causes a liquid to be drawn into the space between two very close and parallel surfaces. This space is known as a capillary gap. It's a very strong force. Not only can a liquid flow sideways or downwards, in a suitable capillary gap, it can flow upwards against the force of gravity. It's capillary attraction that pulls a brazing filler metal through the narrow space between the parent metal surfaces. It's therefore essential that the capillary effect can take place, and to ensure this happens, the correct brazing procedure must be used. This procedure involves carrying out 6 basic steps. Designing a suitable joint for brazing, choosing the filler metal, pre-cleaning the parts to be joined, fluxing, heating the joint and applying the alloy, and removing the flux residue. Each step is vitally important in ensuring quality finished joints, and it's worth looking at each one in detail. The best brazed joints are those designed with a close, uniform capillary gap. The designs for brazed joints are quite different to those required for welding. In each case, the components for brazed joints are overlapped to produce a narrow capillary gap. It's essential that this gap is close and uniform so that capillary attraction can operate. But what exactly does close mean? This graph shows how the strength of a brazed joint varies with the clearance. It's based on joints made in stainless steel using Johnson Matthey Easy-Flow brazing alloy. If the gap is ideal, say 0.05 millimeters, the peak strength is about 900 newtons per square millimeter. Even when the gap widens to 0.125, the joint will not fail at less than 600 newtons. These strengths are far in excess of the requirements for almost any brazed assembly. The way the capillary effect draws the filler metal through the joint can easily be demonstrated using 2 glass plates separated by 0.05 millimeter shims at the top and bottom. If the plates are dipped into a tray of coloured liquid, the liquid is drawn into the capillary gap and fills it completely. This is what happens in a well-designed joint. If the gap is not ideal, the capillary effect will be diminished. In this example, the glass plates are separated by a 0.05 millimeter shim at one end and a 0.4 shim at the other. This time, when the plates are dipped in the tray, the liquid rises only part way. Capillary attraction lifts the liquid until the gap gets to about 0.15 millimeter, but then gravity prevents it rising any further. Achieving the correct capillary gap is not difficult, but it does need special consideration. In the previous demonstration, a T-joint was made by resting one part on another and holding the assembly together with a simple jig. With tube joints, a simple slip fit of one part into the other does the same thing. It gives a uniform gap of about 0.1 millimeter and allows capillary attraction to occur. But there is another aspect to be considered. When a metal is heated, it expands, and some metals expand at different rates to others. If two parts made of the same material are being joined, there's no problem. They expand together and the gap stays the same. But if dissimilar metals are being joined, such as a brass cylinder and a steel plate, allowance has to be made for differential expansion. The capillary gap at room temperature may be quite different by the time the joint reaches brazing temperature. If the joint is machined to provide a clearance of 0.05 at room temperature, by the time it's heated to brazing temperature, the gap will have completely disappeared due to the brass expanding faster than the steel. The problem can be solved by increasing the gap when the parts are cold. Now, when the assembly is heated, the brass expands faster than the steel, reducing the gap to the correct clearance at brazing temperature. If the materials were reversed, an initial undersize gap would be required. This could mean a force fit. Then, as the assembly is heated, the brass again expands faster than the steel, so that the gap is correct at brazing temperature. The amount to allow for differential expansion depends on the metals being brazed. Tables of coefficients of thermal expansion are readily available and should be consulted when designing an assembly. So to summarize, we need the correct joint design, a close and uniform gap, and that gap to be correct at brazing temperature. Now let's move on to the second basic step in successful brazing, the choice of filler metal. There's a wide range of filler metals with different compositions, melting ranges, and other special properties. They're available in a variety of forms, including wire, strip, bare or flux-coated rods, foil, powder, pastes, and all manner of pre-formed parts and rings. The easiest to use alloys are the high-silver free-flowing alloys because of their low melting temperatures and narrow melting ranges. Alloys with higher brazing temperatures and longer melting ranges become increasingly difficult to use. In most of the demonstrations in this video, Johnson Matthey Silver-flo 55 is used. This is a universal low-temperature, free-flowing alloy suitable for almost all applications. It also has the additional benefit of being cadmium-free and therefore reduces the risk of health and safety problems. Let's now move on to the third basic step to successful brazing, pre-cleaning the parent metals. It's essential that the mating surfaces of the components to be brazed are thoroughly clean. Oil, grease, and oxides can all prevent capillary attraction within the joint. This can be demonstrated with the glass plates. As before, the two plates are separated by 0.05 mm shims to give the ideal gap. But this time, there are some greasy marks on the inside surfaces. When the plates are inserted into the tray of liquid, the liquid is again pulled through the capillary gap, but this time it leaves voids around the greasy marks. If this were a joint, it wouldn't be a sound one. Most engineering components need nothing more than degreasing before assembly. A solvent degreasing agent is preferable, but hot soapy water is better than nothing. If surface oxides are present, they can be removed either chemically or mechanically. Mechanical removal is preferable because the surface is roughened and an excellent bond is obtained. A medium-grade abrasive gives just about the right degree of surface roughness. The next step in the process is fluxing. The chemical action of flux is complex, but in essence, it dissolves oxides that form during heating and acts as a barrier to protect the parent and filler metals during the brazing cycle. Flux is a chemical compound, supplied as a powder or a paste. It's always best to use it as a paste. Flux powder should be mixed to double cream consistency with water and a few drops of detergent. It's applied to the joint surfaces with a brush prior to assembly and heating. It's worth remembering that too much flux will hardly ever cause a problem, but too little will result in poor quality joints. The flux also serves as a temperature indicator. This can be demonstrated with this copper plate, which is first fluxed and then heated. At 100 degrees centigrade, the water boils off. At around 300 degrees, the flux begins to turn white and puffy. It's now active and protecting the metal surfaces. At about 600 degrees, the flux becomes clear and runs like water. This indicates that the brazing temperature has been reached. Notice that the section of metal which was not covered by flux has become oxidized and black. By protecting the surface, flux allows the filler metal to wet out onto the parent material and flow smoothly through the joint area. This can be demonstrated by placing a piece of Silver-flo 55 on a copper plate without any flux. The plate is then heated to the melting point of the filler metal. The filler metal melts, but doesn't flow out over the surface of the copper. If the process is repeated, but after the parts have been fluxed, the wire melts and flows smoothly out onto the surface of the plate. Comparing the two plates shows the importance of the flux. Mattiflux 100 was used in most of these experiments. This is a general-purpose flux. Easy-flow powder could have been used after it had been mixed to a paste. For higher temperature operations, tenacity 4A or 5 would be more appropriate. There are many brazing fluxes formulated to meet the requirements of a wide range of applications. Whatever the metals to be brazed, or the method used, there is a Johnson-Matthey flux that will do the job. But there are some occasions when flux is not needed at all, such as when brazing in a protective atmosphere or in a vacuum furnace. It's also unnecessary when brazing copper to copper, provided a filler metal containing phosphorus is used. This can be demonstrated with Johnson-Matthey's Silphos 5. The phosphorus in this alloy forms a compound that acts as its own flux on copper surfaces. If a piece of Silphos 5 is heated on a copper plate without any flux, as it reaches melting temperature, it flows out smoothly over the copper. But unless copper to copper is being joined, or an atmosphere furnace is being used, the fluxing step is absolutely essential. The fifth step in successful brazing is heating the joint and flowing the alloy. After the parts have been fluxed, they have to be held in position during the brazing process. Lighter sections are not self-supporting and need extra weight, like this hold-down bar, to keep them in place. Some joints, such as tubular connections, do tend to be self-supporting. Heavy, flat sections will be held in place by gravity alone. The most common heating method utilizes a handheld brazing torch burning a mixture of either natural gas and air or oxygen and acetylene. The oxyacetylene flame is more intense and is the more widely used of the two. To demonstrate heating technique, this brass rod will be brazed to a steel plate. First, both parts are fluxed and then assembled. The torch gas mixture is balanced to give a slightly reducing flame, rich in fuel gas. This is indicated by the broad feather on the blue inner cone of the flame. The whole assembly is then heated, concentrating on the brass rod because it's a good conductor and tends to dissipate heat rapidly. As the assembly nears brazing temperature, extra heat is applied to the underside of the plate. This is because molten alloy always flows towards the hottest part of the joint. This technique helps to ensure that the alloy flows towards the base of the brass rod, completely filling the joint area. Once the flux is clear and flowing over the joint area like water, Silver-flo 55 brazing alloy is fed into the joint line. It's bad brazing practice to melt the alloy directly with the flame and may cause unsound joints. It can also increase health and safety problems by boiling volatile elements such as cadmium and zinc. The alloy is melted by heat from the components rather than direct heat from the torch flame. As it melts, it flows through the joint, completing the brazed assembly. Copper pipes and fittings, as used in plumbing, refrigerators and air conditioning units, are brazed using a similar heating technique. First, the tube is heated and expanded into the fitting. The whole assembly is then broadly heated. As the components near brazing temperature, the fitting is given extra heat to encourage the brazing alloy to flow into that part of the joint area. In this demonstration, Silphos 5 is being used. As this filler metal contains phosphorus and both components are made of copper, flux is not needed. The alloy flows freely around the joint and penetrates the entire joint area. In this case, a vertical down joint was brazed, and it can be seen how the alloy flows and distributes itself throughout the joint area. Pipe joints may also be brazed in the vertical up and the horizontal positions. In each case, the alloy flows evenly throughout the joint area. Having completed the joint, the last step in the brazing process is to remove the flux residue. Removal of flux residue is usually a very simple process. In the examples demonstrated in this video, all that's needed is a soaking in hot water at about 60 degrees centigrade for a few minutes. Light cleaning with a wire brush after soaking should ensure complete flux removal. If the flux residue is blackened or burnt, it will need to be removed by abrasion or shot blasting. Residue in this condition indicates incorrect heating or the wrong choice of flux. The 6 basic steps of successful brazing have now been completed. These general principles apply to all brazing processes. In these demonstrations, a hand brazing torch was used, but this is not the only method of heating joints. The most common methods are torch heating with either handheld torches or fixed burners, induction heating, or heating in a furnace in either a protective atmosphere or a vacuum. Let's look briefly at the 2 methods not yet covered. In induction brazing, the parts to be joined are placed in a coil through which a high-frequency current is passed. This induces a current flow in the parts to be brazed, which causes rapid localized heating. In this case, a tungsten carbide tip is being brazed into a drill shank. Induction brazing is widely used for this type of application. There are many types of furnace for furnace brazing, using a variety of atmospheres or even working in a vacuum. This continuous belt furnace uses a reducing atmosphere which eliminates the need for flux. The components, again carbide-tip drills, are placed on the conveyor belt at the inlet end of the furnace and pass through various heated zones before emerging minutes later as clean, bright, finished components ready for use. Finally, let's look at some examples of good, properly made brazed joints and see what's special about them. Look at this T-joint. It's neat, the fillet is tiny, and there's no excess filler metal. There's no need for special finishing operations here. Look at this cornet. The joints are invisible. A brazed joint is strong and ductile. It can be bent without fracturing. The tensile test shown earlier in this program showed just how strong a joint can be. Tube joints are leak tight. This is critically important when manufacturing products such as heat exchangers. They work in pressurized circuits where a leak in any one of the joints could prevent the whole system from working. Every unit is pressure tested to ensure 100% leak-tight joints. Brazing is also the most useful process when joining dissimilar metals. As long as the